Okay, good afternoon. So, this is our 34th lecture of the course Compressible Flow and Gas Dynamics, and today we will start a discussion on particularly taking the help of one special type of flow which is called as irrotational flow. Okay, so if our flow in any situation is irrotational, then what we can do, actually we can take the help of velocity potential function. Okay, so we can take the help of velocity potential function to solve irrotational flow situation. So this makes actually our analysis little bit simpler. Okay, so first we will quickly recapitulate the concepts of basic fluid dynamics related to the irrotational flow. So if we see that we are having a flat plate and flow of viscous fluid is happening over this flat plate, then we will be having certain boundary layer region over here where our velocity will be something like this. Okay, so this will be, say, velocity profile over here. So for this type of situation, if I consider the curl of a velocity vector, so that will not be equal to 0. So it means this is nothing but a rotational flow situation. Similarly, we have seen that while we discussed about the Crocos theorem, so we found in case of Crocos theorem that if I have some blunt shaped object, and ahead of this object, if I have the formation of a shock wave which is having more strength near the object and far away from it, if its strength decreases, then once again also we will be having situation of a rotational flow. Okay, our flow will not be irrotational. Then we have also seen a number of situations where our actually flow was nothing but irrotational. For example, if we talk about the case of flow over a wedge shaped structure, so in this case we found that we are having a shock wave, but the strength of this shock wave is remaining the same everywhere. So that's why we are getting nothing but situation where our curl of velocity vector is equal to 0. Similarly, for internal flow situations also, so if I have a convergent divergent nozzle which is nothing but a variable area conduit, so in this case also our flow was nothing but irrotational. Okay, similarly if I take I have told you earlier also, if I take very slender objects, so if I have object with sharp tip and it is very thin, its thickness is small and length is long actually, so though in this type of situation I will be having a wave which will be having slight curvature, however the strength of the wave will not be that much different. So we can, though here curl of V will not be exactly equal to 0, but it can be approximated nearly equal to 0. So if we are having slender objects with sharp tip, for these things also we can apply nothing but the irrotational flow theories. Okay, now what are the necessary conditions for irrotational flow? So as we have seen that for irrotational flow, del cross V vector has to be equal to 0. So if I take this one, then I will be having a cross product of this. So del by del x, del by del y, and del by del z, and say velocity vector is having component Vx, Vy, and Vz. These are the components in x, y, and z direction. So curl of this will comes out to be I cap into del, tell me, Vz by del y minus del Vy by del z. Is it fine? Minus of j cap into del Vz by del x minus del Vx by del z plus k cap times del of Vy by Vx minus del of Vx by del y, and this entire has to be equal to 0. Okay, for an irrotational flow situation. So it means if this entire is 0, then individual component has also to be 0. So rotations in individual directions would also be 0. So from here I can say that for irrotational flow, del v z by del y has to be equal to del vy by del z. Similarly, second situation, del vz by del x is equal to del vx by del z, then del vy by del x has to be equal to del vx by del y. So these are nothing but I can call these as the necessary boundary conditions for irrotational flow. Okay, so for irrotational flow these conditions must satisfy. Okay, so these are the necessary conditions for irrotational flow. Now if I typically take the case of momentum equation, okay, so our momentum equation is nothing but rho into dv vector by dt equal to minus gradient of p. So over here I have neglected the viscous and body forces. So this type of momentum equation is called as Euler's equation. Okay, so if I take Euler's equation, then over here what I can do, I can write x momentum equation, particularly rho times vx into, let's write x momentum equation for steady flow situation. Okay, so if I write for steady flow situation, then the time term over here will be equal to 0. So I will be having only the spatial term. So del vx by del x plus vy into del vx by vx or vy by vx, vy by, what will be here, tell me, vx by vy, okay, plus vz into del vx by del z equal to minus del p by del x. Okay, so this is nothing but my x momentum equation. Okay, so now what I can do, I can write over here minus del p by del x, I have multiplied it with dx, that is equal to rho times vx into del vx by del x plus vy into, now for irrotational flow situation, in place of del vx by del y, I can write del vy by del x. Okay, so del vy by del x plus vz times, in place of del vx by del z, del vx by del z, what I can write, del vz by del x. Okay, so and outside I have taken dx over here. Okay, so this has become minus del p by del x into dx equal to rho times, here what I can do, this vx and this vx, I can write del by del x of vx square by 2. Okay, so by 2, say I am taking outside with rho by 2. Okay, and similarly I can write plus del by del y of vy square plus del by del z of vz square, because y2 I have just now taken outside. Say this is my equation number 1. Okay, the way I have written this x momentum equation, particularly for nothing but my particularly for irrotational flow. Okay, in the similar way I can write my y momentum equation del p by del y of dy equal to rho by 2 into del by del x of vx square plus del by del y of Vz square into dx. Fine. Is this point clear? So I will be having y momentum equation. Similarly, I can write down the z momentum equation. So that will be minus del p by del z dz. Here I have to write dy here. So that will be equal to rho by 2 del by del x of, sorry, this I have made a mistake. This should be y square, okay, and this will be y in first equation. Oh, not x, vy. Here you are saying. Equation number 1. These two terms you are saying. What will be there? Okay, yeah, sorry. Denominator is del x. Yes, all are del x. Yes. So in the similar fashion, if you write, then these all will be del y. Yeah, this is the mistake. Yes, correct. From here to here, I have written wrongly. Yeah. So this entire is del y. So now it will be actually Vx only. Similarly, here I will be having del by del z Vx square plus del by del z Now if I add these three equations and take the minus sign on the right hand side, what I will be getting? Del p by del x into dx plus del p by del y into dy plus del p by del z into dz equal to minus rho by 2 del by del x of Vx square plus Vy square plus Vz square. Similarly, I will be having plus del by del y of, here I will be having dx also, Vx square plus Vy square plus Vz square into dy, and here I will be having del by del z of Vx square plus Vy square plus Vz square into dz. Okay, so this is typically nothing but the definition of a, what are these quantities? This whole is nothing but equal to v square. This is also v square and this is also v square. So what ultimately I can write, and this is the definition of a total derivative. Okay, so from here I can write total derivative of pressure is equal to minus rho by 2 into this will be becoming total derivative of v square. So total derivative of v square over here. Okay, and ultimately if I take d of v square, then it will be becoming minus rho v into dv. Okay, so this is nothing but the representation of Euler's equation in some different form, and this typical equation we have obtained over here. Okay, so why we have got this? Because later on we will be using this equation. Here we will be using, now our next task will be, when we analyze a flow situation, we are having three different equations: continuity, momentum and energy equation. So all these three equations, continuity, momentum and energy, we will try to form a single equation. Okay, and that single equation is called as nothing but the velocity potential equation. So now our attempt is to determine the velocity potential equation. Okay, now one simple thing you can deduce from the previous expression So here you can see when your dP is positive, corresponding to that your dV is negative. So it means that in any situation, if your pressure is increasing, your velocity will decrease, and if your dP is negative, then dV is becoming positive. Okay, so the point is, if you take any fluid element, and in this fluid element, if P is the pressure over here, and here if pressure is P plus dP, and our dP is negative, in that case what will be happening? Net force will be acting on the fluid element in the rightward direction, and fluid element will be accelerating in this particular direction. Okay, so this type of situation is called as favorable pressure gradient. Okay, and if the situation is reverse, that dP is positive, then this pressure will be more, so net force will be in the leftward direction, and if fluid element is having some initial velocity v, it will try to deaccelerate. So this is called as adverse pressure gradient. So this is nothing but the, you can say, representation of our Bernoulli's equation, because Bernoulli's equation says the same thing. But if you have to apply this equation, so either this can be applied for irrotational flow field, or it can be applied only along a single streamline. So these are the two important points. Okay, so when we talk about velocity potential equation, so we first take the help of the vector calculus. Okay, so as per the vector calculus, if I have any v vector, so what I can do, if my curl of v vector is equal to 0, then I can say that this v vector will be nothing but equal to gradient of some scalar. Okay, why? Because we know from the vector calculus, the property is that curl of gradient is equal to 0. Okay, so that property comes from, so if it is curl of gradient, then this gradient should apply on nothing but a scalar parameter. Okay, so if I have any vector quantity whose curl is equal to 0, so that vector quantity can be represented in terms of gradient of a scalar quantity. Okay, so when we do so, we represent this particular scalar is called as velocity potential function. Okay, now our v vector will be nothing but equal to Vx at I cap plus Vy at j cap plus Vz at k cap. Okay, so this will be equal to del by del x, gradient of phi, so del by del x, del phi bar by del x I cap plus del phi bar by del y j cap plus del phi bar by del z k cap. So from here our simple approximation is that Vx can be written as del phi bar by del x, Vy can be written as del phi bar by del y, and Vz can be written as del phi bar by del z. Okay, so now we will try to utilize this information to write down a single equation out of continuity, momentum and energy, and that equation we call as nothing but the velocity potential equation. Okay, so now our continuity equation for steady flow situation is nothing but divergence of rho v vector is equal to 0. Okay, so in algebraic form, in differential form, I can write it in terms of del by del x of rho vx plus del by del y of rho vy plus del by del z of rho Vz equal to 0. Okay, so now this can become rho times del Vx by del x plus rho times del Vy by del y plus rho times del Vz by del z plus Vx times of del rho by del x, Vy times of del rho by del y plus Vz times of del rho by del z equal to 0. Okay, so now we know that our Vx is equal to del phi bar by del x. So let's call it as nothing but phi bar of x. So similarly, if you do del Vx by del x, that will be becoming double derivative of this. So phi bar double x is a representation of nothing but del square phi bar by del x square. Okay. So if I do these substitutions over here in my continuity equation, so what I will get, rho times phi bar xx plus phi bar yy plus phi bar zz plus phi bar x of del rho by del x plus phi bar y of del rho by del y plus phi bar z of del rho by del z equal to 0. Okay. So ultimately, say this is my equation number 4. So in this equation 4, if I see, I have two additional terms. What I want my complete equation in the terms of velocity potential function. Okay. So I don't want more variables in my formulation. Okay. So if I want to write this equation entirely in the form of a single variable, so here rho is one additional variable and these gradients of rho in different directions, these are the three additional variables. So we have to now get some equations which can actually remove these things. So earlier, if you recall, just now we have derived one equation that dp is equal to minus rho by 2 d of v square. So this is nothing but equal to minus rho by 2 d of vx square plus vy square plus vz square. So I can replace now this dx vx with phi bar x. Okay. So it will be becoming phi bar x square plus phi bar y square plus phi bar z square. Say this is equation number 5. Okay. Now another important point is, we know that del p by del rho for an isentropic flow situation is nothing but equal to a square. Okay. So typically whenever we study the irrotational flow, from Crocos theorem also you can see, for irrotational flow our entropy gradient will be equal to 0. Okay. So irrotational flows are nothing but of isentropic nature. So considering that entropy is a constant only, what I can do, I can write this a square in terms of dp by d rho only, because for a typical isentropic flow I will not be having any dependence of parameter entropy, because entropy is remaining constant. So if entropy is remaining constant, so this partial derivative I can write directly as a total derivative dp by d rho. Okay, because all irrotational flows are nothing but isentropic in nature. Okay, so from here d rho will be becoming equal to dp by a square. Okay, so d rho will be dp by a square. So now dp I have calculated, so I got minus rho by 2a square into phi bar x square plus phi bar y square plus phi bar z square. This is my equation number 6. Okay, so I have calculated the value of d rho over here. But what I want to calculate? I have to calculate del rho by del x, del rho by del y and del rho by del z. So these are the quantities which I need to calculate. Okay, so how I can calculate these quantities? What I can write for d rho? D rho is nothing but total derivative. So this d rho I can write as del rho by del x into dx plus del rho by del y into plus del rho by del z into dz. This will be equal to, sorry, one mistake I have done here, there will be one d also. Okay, so then minus rho by 2a square and then I will be having d of phi bar x square. Okay, so what I can write? I can write del by del x of phi bar x square plus phi bar y square plus phi bar z square into dx plus del by del y of phi bar fine. So from here, ultimately if I compare the different terms, then I can say my del rho by del x will be equal to minus rho by 2a square, okay, and del by del x of phi bar x will become 2 phi bar x into phi bar double x, okay, plus 2 phi bar y into phi bar xy plus 2 phi bar z into phi bar xz. Fine. This will be my del rho by del x over here. So ultimately I am getting 2 will cancel, minus rho by a square of minus rho by a square of phi bar x into phi bar xx plus phi bar y into phi bar xy plus phi bar z into phi bar zx. Similarly, I can calculate del rho by del y and del rho by del z. So tell me what will be del rho by del y. Say this is equation number 7. Now tell me what will be del rho by del y. Minus rho by a square into, I have to take del by del y of this. Okay. So it will be 2 times of phi bar x into phi bar xy, sorry, 2 I am cancelling with outside, okay, plus phi bar y into phi bar yy plus phi bar z into phi bar zy, okay. This is equation number 8. Similarly, I can write del rho by del z equal to minus rho by a square into phi bar x into phi bar zx plus phi bar y into phi bar zy plus phi bar z into phi bar zz. Okay, so this is equation number 9. Now what I can do, this is my equation number 5, sorry, equation number 4. In equation number 4, I can divide throughout by rho, and I will replace this del rho by del x, del rho by del y and del rho by del z. Okay, so I will be substituting now. I will be doing 4 by rho and then substitution of 7, 8 and 9, and then after doing rearrangement of different terms, ultimately what I will get, 1 minus phi bar x square by a square, okay, into phi bar xx plus 1 minus phi bar y square by a square into phi bar yy plus 1 minus phi bar z square by a square into phi bar zz, okay, minus of 2 times phi bar x, phi bar y into phi bar xy by a square minus of 2 times by a square phi bar y phi bar z into phi bar yz minus 2 times by a square phi bar x phi bar z into phi bar zx equal to 0. Okay, so this important equation is called as velocity potential equation. Okay, still this equation is having one issue. Okay, so still it is not completely in terms of phi, it is having one more term involved over here, and that term is nothing but a square. Okay, where a is actually nothing but the speed of sound, and when you are talking about a flow field, then depending upon the fluid local properties of the fluid at different parts in the flow field, speed of sound will also be different. So this is nothing but a variable or unknown quantity at the moment. Okay, so ultimately we have to represent this speed of sound also in terms of potential functions. Okay, so for that we will take the help of energy equation. So say this is my equation number 10. So typically our energy equation says that H plus V square by 2 is equal to H naught. Okay, and for isentropic flow situation, H naught remains constant. Isentropic and steady situation. Okay, for steady flow situation and isentropic situation, it remains constant. Okay, so that you can recall from the previous lectures when I have discussed about the different forms of energy equation. So in one of the form of energy equation, if we neglect the body force, heat transfer, and make phenomenon as steady, then H naught remains constant. Okay, for a steady flow situation. Now this can be written as, for calorically perfect gas, Cp into T plus V square by 2 equal to Cp into T naught. Okay, now Cp can be written as gamma R by gamma minus 1. Okay, and so it will become a square by gamma minus 1 plus V square by 2 equal to a naught square by gamma minus 1. So from here I can say that my a square is nothing but equal to a naught square plus gamma minus 1 by 2 into V square. Okay, and what about V square? V square I can write as Vx square plus Vy square plus Vz square. Okay, so from here ultimately I will get a square equal to a naught square plus gamma minus 1 by 2 into, in place of Vx I can write phi bar x square plus phi bar y square plus phi bar z square. So this is another important equation which actually gives the relationship in between A and velocity potential functions. So say this is my equation number 11. Yeah, here it will be minus sign. Yes. Okay, so now if you see jointly equation number 10 and equation number 11, so ultimately you can replace a square in equation number 10 with this equation where a naught is nothing but a constant, because h naught is constant for a flow situation, so a naught will remain the fix. So only thing we will be having variable as velocity potential function, and entire speed of sound we have written in terms of the velocity potential function. So now till now I have not taken any approximation except from the consideration of irrotational flow. So if I have any rotational flow, what I can do, I can solve the velocity potential equation number 10 and this equation number 11 jointly and determine the values of phi for the entire flow field. Okay, so my solution algorithm will be solve equations 10 and 11 jointly. Okay, and with then number 2, once we have solved these equations, then I can determine, I am knowing the value of phi at all the points. Then what I can do, I can calculate Vx, Vy and Vz. Then what I can do, I can take the help of equation 11 to calculate A, speed of sound. Once speed of sound is there, then what I can do, I can calculate Mach number equal to V by A. Once I have Mach number equal to V by A, then in terms of the upstream Mach number, already we have derived different relations for solving our compressible flow situation. If I know the upstream Mach number, I can calculate the pressures, temperatures and density etc. using the shock wave relations. Okay, so it means that whatever analysis we have done, if I have unknown flow field, so for that unknown flow field I can simultaneously solve equation number 10 and 11, and from these equations I can actually determine the complete flow field. But one important point is there, if you see typically the equation number 10, this is nothing but a non-linear equation. Okay, so there are three things now. Due to the non-linear nature of this equation, either what we can do, due to non-linear nature, either we have to solve this equation numerically, okay, using the numerical methods. Second approach is we can make this equation nothing but linear also. Okay, so for making this equation linear, further there are two approaches. First approach is that we will be doing some coordinate transformation from one space to another space, so that some of the terms are getting vanished and we are getting our linear equation. And second thing is we will be keep on solving this in XYZ coordinate system only, but we will try to find out the terms which are of lesser magnitude, which are not relevant for a given physical flow situation. We will remove these terms so that finally we can get nothing but the linear set of equations. Okay, so over here, whatever equation number 10 I have derived, this is a very generic equation and it is of non-linear nature, so it is applicable for any type of flow situation. For example, in case of compressible flow, subsonic flow, supersonic flow, transonic flow and hypersonic flow. For all the four types of flows it is applicable. Okay, but the only difficulty is with the solution of this equation, because it's a non-linear, so we will not be able to find out the analytically closed form solution. So we have to go for either numerical solution or we have to linearize this equation. Okay, so particularly for subsonic and supersonic flows, we can actually linearize this equation by making certain assumptions of small perturbation theories. So that part, let's try to see how we can do that. Okay, so now we will try to get linearized velocity potential equation. And what is the benefit of this velocity potential equation? The benefit is that if we are able to relate the closed analytical form of solution, then within very less time, okay, we will be able to get the solution fast. Okay, so once we are having fast solution, then we can observe the trends. Okay, so that is why actually, though with the advent of computers now, use of this equation is not that popular, but still in order to validate the trends from our numerical simulations, actually we still use this method so that we can quickly get the solution and then compare that. Okay, so this linearized velocity potential equation, particularly as I told you that this linearization can only be done if we are having actually applicability of small perturbation theories. Okay, so when we are talking about the small perturbation theory, so whatever our mean flow is there, the deviation from mean flow should be very, very minimal. Okay, so for that, that is the reason that majorly this type of linearized velocity potential equations are applicable for slender objects only. Because if you go for non-slender objects, there your perturbations will be large, and then this type of linearized theories will not be applicable. Why? That mathematically we will be proving now. Okay, so if we have slender object something like this, say this is object with sharp tip but very thin in thickness. Okay, so like our airfoil structure. So airfoil structure is also thin and actually slender. Okay, so in this type of situation, say we may get some shock waves, something like this, but ultimately because it is very thin, so what I can do, I can assume that this will be nearly equal to 0. So flow situation will be irrotational. Okay, now for this flow situation, say my free stream is moving with parallel streamlines and having velocity v infinity. Okay, now when the flow will be coming over it, it will be having certain perturbation. Okay, so it was coming horizontal, but now it has perturbed slightly. So say the velocity vector at any point of time is something like this. This is my v vector over here, perturbed velocity vector. Okay, now typically if I have to write the velocity vector at any local field, at any local location, that will be vx I cap plus vy j cap plus vz k cap. Okay, the local components of the velocity. Now you can see that this velocity field initially is v infinity in x direction, and in y and z direction it is v infinity y is equal to 0, which is equal to v infinity z. So in y and z direction we don't have any free stream velocity. So free stream velocity initially was only in x direction. So if I say that when I have placed this object, after placing the object, my changes in the or perturbations in the velocity field are vx dash, vy dash and vz dash. So vx dash, vy dash and vz dash are nothing but the changes in the velocity field when I have introduced this object over here. Okay, so then what I can do, I can write my vx as nothing but initial velocity in x direction was v infinity, and perturbation because of the object is vx dash. So I can write v infinity plus vx dash is the velocity in. Initially there was no velocity in x direction, but this perturbation has given some velocity in y direction now. Okay, so vy dash into j cap plus vz dash into k cap. So this is my velocity field over here. So now in this velocity field, if I consider that these perturbed values are nothing but of very small in magnitude. If we consider these perturbations are small in magnitude, then I can call this type of analysis, whatever we will be performing, as nothing but theory of small perturbations. That analysis I will be calling as theory of small perturbations. Okay. Now physically what we have done, physically we have taken a thin slender object. So as we have taken a thin slender object, so it will try to create a situation of very small perturbation. Okay, if you take a thick object, then perturbations, because deformation of the streamline will be very large. If there is large deformation in the streamline, then our perturbations will be of finite magnitude in velocity in all the three directions. Okay, then this type of linearized theories cannot be applied. Okay, so now we know that V infinity is nothing but velocity in x direction, but this V infinity I can write as del phi bar by del x. Okay, and total velocity in, sorry, let's not do this. So what we have, total velocity in x direction, if you see from this velocity field now. Okay, so total velocity in x direction is V infinity plus Vx dash. Okay, so Vx, total velocity in x direction, can be written as V of phi bar by, sorry, del of phi bar by del x. That will be equal to V infinity plus, let's consider that these fluctuating components Vx dash is represented by some another velocity potential function, which is phi. Okay, so phi is the potential function which is only for the perturbation part. Okay, similarly Vy dash will be del phi by del y, and Vz dash will be del phi by del z. Okay, so from here I can write this Vx dash as nothing but equal to del phi x by del x. So this phi bar is nothing but corresponding to the total velocity, and this phi is corresponding to only the fluctuated component which has been, or the perturbed component which has been introduced due to the presence of this solid object in the flow field. Okay, so typically this my velocity vector over here, this velocity vector can be represented with gradient of phi. Okay, and this gradient of phi will become V infinity plus Vx dash in I cap plus Vy dash in j cap plus Vz dash in k cap. So from here also you can see the expansion of this will be del phi bar by del x in I cap plus del phi bar by del y j cap. So from here also you will be finding that del phi bar by del x is nothing but equal to V infinity plus, if I write Vx dash with del phi by del x. Similarly, del phi bar by del y from here will become del phi by del y, and del phi bar by del z will become nothing but del phi by del z over here. Okay, so now single derivatives we have expressed. Now I can also express the double derivative. So phi bar x will become, the derivative of V infinity with x will be 0, and this derivative will become phi of xx. Similarly, phi bar of yy will be equal to phi of yy, and phi bar of zz will be equal to phi of zz. So the difference between phi bar and phi is, phi represents the potential functions for the perturbed portion, and phi bar represents the potential function for the total velocity. Okay, so now if you see what we had, our entire velocity potential equation number 10, that was in terms of phi bar. Okay, so I can now replace each phi bar in velocity potential equation number 10 with these equations in terms of phi. Okay, so now let's do one thing. We will be multiplying equation 10 with a square, and we will be replacing phi bar terms with phi. Okay, if we do these replacements and then little bit of rearrangement, ultimately we will be getting one equation which is a square minus V infinity plus del phi by del x whole square into del square phi by del x square. Okay, plus a square minus phi y square into phi yy. Okay, So now I am writing it in the short form. Plus a square minus phi z square into, not phi bar, phi z. Okay. Minus of 2 times v infinity plus phi x into phi y into phi xy, minus of 2 times v infinity plus phi x into phi z into phi xz, minus of 2 times phi y phi z into phi yz. So this is the entire equation number 10, but this equation is now in the form of, this equation is purely now in the form of phi. Okay, where phi is nothing but the perturbed component, because v infinity we already know. So if we simply solve it for the perturbed portion, then that perturbed portion we can add to v infinity, particularly in x direction, and in other direction our solution will be as it is. Okay. So still we have now replaced our equation from phi bar to phi, but still this equation is nothing but a non-linear. Okay. And another important point is also there. This equation can also be written in terms of, say, if del phi by del x I write with Vx dash. So then in terms of Vx dash and Vy dash, this equation can be written as, let's write, that is also an important form we will be using later on. So a square minus V infinity plus Vx dash whole square into del Vx dash by del x plus a square minus Vy dash square into del Vy dash by del y plus a square minus vz dash square. So what I am doing, wherever I am having del phi by del y, that I am replacing with v dash y. Wherever I am having phi double dash phi yy, that I am replacing with del y dash by del y. Okay, so just I am doing substitutions from phi to in terms of velocity. Okay. Okay, so say this is equation number 13. So nothing but wherever phi was there, that I have presented in terms of the velocities. One important point is there, in my equation number 12 and 13, a parameter is still in terms of, is still unknown. This we have not yet expressed in terms of, in terms of either vx dash, vy dash, vz dash, or in terms of phi. Okay, so we have to do that. So how we can do this? If we have to do this, then we have to present it by taking the help of energy equation. Okay, so energy equation will tell that h infinity plus v infinity square by 2 will be equal to h plus v square by 2. Okay, so h infinity plus v infinity square by 2 can be written as h plus 1 by 2 of v square. V square will become v infinity plus vx dash square plus vy dash square plus vz dash square. Okay, so this will be simply becoming like this. Now this quantity h infinity, we already know it can be written as a infinity square by gamma minus 1 plus v infinity square by 2 equal to, this can be written as a square by gamma minus 1 plus 1 by 2 of, now let's split this, so it will be becoming v infinity square plus vx dash square plus 2 times v infinity v x dash plus vy dash square plus v z dash square. Okay, so ultimately what I will be getting, that a square is nothing but equal to a infinity square minus of gamma minus 1 by 2. Okay, and inside I will be getting 2 times v infinity vx dash plus vx dash square plus vy dash square plus v z dash square. Okay, is this point clear? So now say this is my equation number 14. This is equation number 14. Now equation number 14 gives me the value of a square, and equation number 13 is written purely in terms of velocities. Now if I substitute equation number 14 into equation number 13, okay, and then ultimately if I rearrange, what I will be getting, I will be getting one final equation which is very big, and it is 1 minus m infinity square. Now can you tell me what is m infinity? V infinity by a infinity. This is a known parameter because we know the free stream velocity, we know the speed of sound corresponding to that. Okay, into del vx dash by del x plus del vy dash by del y plus del v z dash by del z, that will be equal to m infinity square, and here I will be having gamma plus 1 into vx dash by v infinity plus gamma plus 1 by 2 into vx dash square by v infinity square plus gamma minus 1 by 2 vy dash square plus vz dash square by v infinity square, and outside del vx dash by del x. Okay, similarly I will be having next term m infinity square into gamma minus 1 vx dash by v infinity plus gamma plus 1 by 2 into vy dash by v infinity vy dash square by v infinity square. Okay, plus gamma minus 1 by 2 into vz dash square plus vx dash square by 2, sorry, by v infinity square, and bracket, and outside this bracket del vy dash by del y. Okay, and then we will be having plus m infinity square gamma minus 1 vx dash by v infinity plus gamma plus 1 by 2 vz dash square by v infinity square plus gamma minus 1 by 2 vx dash square plus vy dash square by v infinity square and whole del v z dash by del z plus m infinity square into vy dash by v infinity into 1 plus vx dash by v infinity del vx dash by del y plus del v y dash by del x plus vz dash by v infinity into 1 plus vx dash by v infinity del vx dash by del z plus del v z dash by del x plus of vx dash vz dash by v infinity square into del vz dash by del y plus del vy dash by del z. So this is the entire equation. After doing these previous substitutions, this is the entire equation, and this entire equation you can see purely is in the form of perturbed quantities. Okay, now we can take some assumptions over here. So till now we have not introduced any assumption. Okay, till now mathematically, though physically we are initially saying that our vx dash, vy dash and vz dash are small, but till now mathematically we have not neglected these. So now it is time to neglect these parameters. So what we will do, we say that vx dash by v infinity comma vy dash by v infinity comma vz dash by v infinity are smaller than 1. So ultimately what will be happening? Vx dash square by v infinity square, comma vy dash square by v infinity square and v z dash square by v infinity square will be even very smaller than 1. Okay, this is the first condition. Second condition is when my Mach number m infinity is varying from 0 to 0.8 and if it is greater than 1.2. In this region, we will be finding that m infinity square times gamma plus 1 vx dash by v infinity plus so on up to, so this entire term where del vx by del x is there, that will be very small in comparison to 1 minus m infinity square del vx dash by del x. This is second condition we are introducing, that within this range of Mach number, if we do, then we will be finding like this. Similarly, if my Mach number is m infinity is less than equal to 5, then for that situation also what I will be finding, m infinity times m infinity square times gamma minus 1 vx dash by v infinity plus so on up to del by dash by del y will be very small in comparison to del by dash by del y. Okay, another term m infinity square gamma minus 1 vx dash by v infinity into del v z dash by del y, this will be also very small in comparison to del v z dash by del z. Okay, and third term m infinity square gamma minus 1 m infinity square into vy dash by v infinity into 1 plus vx dash by v infinity into del vx dash by del y plus del vy dash by del x. This entire term will be nearly equal to 0. Okay, so once we put these along with these two conditions, these assumptions, what ultimately I get? Ultimately I get 1 minus m infinity square into del v x dash by del x plus del v y dash by del y plus del v z dash by del z equal to 0. Or in terms of velocity potential function, I can say 1 minus m infinity square into del square phi by del x square plus del square phi by del y square plus del square phi by del z square equal to 0. So this is nothing but our linear velocity potential equation. Okay, but this is not now exact equation. This is now approximate equation. What is the approximation we have introduced now? The approximation we introduced is that our perturbations, because mathematically we have introduced the assumption that Vx dash, Vy dash and Vz dash are small. When these are small, then I am getting this equation and it is now a linear equation. Okay. So another important point is this linear equation is not applicable for which types of flows? Transsonic and hypersonic flow. If you see the first condition, m infinity from 0.8 to 1.2, this is nothing but our transsonic flow, and m infinity greater than 5 is hypersonic flow. So it means linearized small perturbation theories you can apply only for the subsonic and the supersonic flows. Okay, mathematically we are finding a regime of Mach number which is particularly matching for transsonic and hypersonic flows where this equation cannot be applied. And physically, if you see, in case of transsonic flow, we find that our problem is strongly dependent upon the geometry, because transsonic is nothing but the condition of transition. So near the condition of transition, if you make slight changes in the geometry of the flow problem, you will be finding your perturbations will be huge. There will be significant changes in the perturbation. So the physical nature of the flow is actually non-linear, which is mathematically creating non-linear situation over here, particularly in that range of Mach number. Secondly, for hypersonic flows, we know that near the hypersonic flow, we will be having very thin shock layer region, and in that shock layer region we will be having very extremely high temperatures, because of which the gases will either go through the chemical reactions or will ionize. Okay, so when the chemical reaction or ionization is there, once again the phenomenon is actually non-linear. So the physical phenomenon is non-linear, and mathematically also we are finding when we are keeping Mach number greater than 5, then this linearization theory is not working. Okay, so you can see a strong connection in between the theory and the mathematics. Another important point is, that I forgot to tell you earlier, let me discuss now. So here, if you see the original equation which we have derived, it was equation number, this is the original equation. Okay, so this equation number 10 is something which is now applicable for compressible flow situation. If I introduce the assumption of incompressibility, what is the assumption of incompressibility? A will be very large. For incompressible flow situation, A will be huge. So our A will be approaching to infinity. If A is approaching to infinity, then this term and this term and all these terms are becoming 0. And if I just write this equation for incompressible flow situation, I will be simply getting phi bar xx plus phi bar yy plus phi bar zz equal to 0. So all these terms are nothing but second derivative, that is becoming equal to 0. So I will be getting a simple Laplace equation. So if you go and check to your basic fluid mechanics course, in case of basic fluid mechanics, when we replace our continuity equation with potential function, what we get? Del square phi by del x square plus del square phi by del y square plus del square phi by del z square equal to 0. So same thing, when we introduce over here the assumption of incompressible flow, then ultimately what I am getting is nothing but the Laplace equation for the velocity potential function, which we have seen in our basic fluid mechanics. So the point is, if you take the more generalized case, from more generalized case you can actually deduce all the individual forms for all special cases. Okay, and second important point is, when we do linearization on this equation, then ultimately we get this linear approximate equation. Why we are calling it approximate? Because this will be only applicable when perturbations are small. And second important point is, this is applicable only for subsonic and supersonic flows. So this cannot be applied for transonic and hypersonic flows. Okay, and ultimately we found that physical nature of the hypersonic and transonic flows is such that which will not lead to the mathematically linearity. Okay. Okay, so I will stop at this point, and in next lecture we will practice some of the physical situations based on this equation. Okay.